So today we're going to tackle what is, without a doubt, the biggest challenge in all of science, the search for a theory of everything. We're talking about a single, beautiful idea that could explain our entire reality, from the tiniest particle to the biggest galaxy cluster.
And really, this whole quest, this whole journey, it all comes down to one single question. This is the thing that keeps physicists up at night, the reason they fill up gigantic blackboards with equations, all in the hope of finding that one master key to unlock the universe.
You see, for about 100 years now, physics has had this split personality. We have two incredibly successful theories, but they're like two different kings ruling over two separate kingdoms. On one side, you have general relativity, the undisputed king of the cosmos, the big stuff. And on the other, you have quantum mechanics, the master of the microcosm, all the tiny stuff.
First up, you've got general relativity, Einstein's masterpiece. It just completely flipped our whole idea of gravity on its head. It says gravity isn't some spooky force pulling things together. Nope, it's actually the shape of space and time itself being warped. You've probably heard the analogy. Imagine a bowling ball on a trampoline. That's what planets and stars do to spacetime. And this theory works perfectly for describing the beautiful cosmic dance of planets, stars, and galaxies. It's all smooth and predictable.
And then you dive into the quantum world. This is where things get really, really weird. Quantum field theory tells us that at the tiniest scales, reality is this buzzing, chaotic sea of energy fields. And the particles we think of as solid little balls, they're not. They're just little ripples, little vibrations in these fields. It's a world of probabilities and jumps, but man, is it accurate for describing how all the subatomic bits and pieces of our universe work.
Okay, so here's the kicker. Both of these theories are absolutely fantastically correct. We've tested them to an insane degree. But they can't both be the final answer, because when you try to use them in the same place at the same time, well, the math just falls apart. The universe, as we understand it, just breaks.
There are a couple of places in the universe where these two domains just violently collide. We're talking about the insane density inside a black hole and that very first moment of the Big Bang. In these places, you have a massive amount of gravity crammed into a teeny tiny space. So you need both general relativity and quantum mechanics to figure out what's going on. And that's where everything goes wrong.
And when physicists try to run the numbers for these places, the equations just break. They spit out nonsense, answers that go to infinity. Think of it like trying to divide by zero on a cosmic scale. It's a huge red flag that tells us, hey, something fundamental is missing from our picture of reality. There's a piece of the puzzle we just don't have yet.
So what do? How do we build that bridge between these two giants of physics? Well, this is where the real fun begins. To solve this problem, physicists are now exploring some of the wildest, most out-there ideas you can imagine. Ideas that question the very nature of space and time.
Right now, there are kind of three main highways that scientists are traveling down, all hoping to get to the same destination. You've got the string path, the space-time path, and the information path.
Okay, first up, the one you've probably heard of, string theory. The basic idea is actually kind of beautiful. What if all the fundamental particles we see aren't little dots, but are actually tiny, vibrating loops of energy, like microscopic guitar strings? A different vibration gives you a different note, an electron, a photon, a quark. It's a really elegant attempt to unite everything.
Path number 2 takes a totally different route. Instead of tweaking the particles, it says, hey, maybe the problem is with space and time itself. This is the idea of quantum gravity. It suggests that if you could zoom in, way in, you'd see that the smooth fabric of spacetime is actually made of tiny, indivisible chunks, like pixels on a screen. The universe is digitized.
And then there's the third path, and honestly, this one is the most mind-bending of all. It asks a really profound question. What if gravity and space-time aren't fundamental at all? What if they're emergent? Think about it like this. A single water molecule isn't wet. Wetness is something that happens when you get a whole bunch of them together. Maybe gravity's like that, a group behavior that comes from something much deeper.
And that idea leads us to something really exciting, captured in this equation here. Now, don't get hung up on all the Greek letters. Just focus on that new bit on the right side, the Qμ term. That Q represents quantum entanglement, that spooky connection between particles Einstein talked about. This theory is basically saying that the geometry of spacetime itself, that's the left side, is literally created by all these quantum connections. It's not a stage for the universe to play on. It's a fabric woven from quantum information.
And if this is true, it could solve huge mysteries. It might even get rid of the need for dark matter, suggesting that the extra gravity we see is just a weird effect of this deep entanglement. It's a huge idea. Okay, but this isn't all just wild speculation and scribbles on a chalkboard. This is a real quest. Physicists are actively scanning the skies, looking for clues, for any little hint from the cosmos that can tell us which of these paths is the right one.
I mean, just get a load of this number. Over 1.2 million. That's how many quasars were just cataloged in a recent survey. By mapping where these super bright, super distant objects are, we are building the most ridiculously detailed 3D map of the universe ever. And we're combing through it, looking for the tiniest little hiccup in gravity that could point to new physics.
And we're not just looking with our eyes, we're listening too. We have this amazing suite of cosmic tools. You've got the Gaia satellite mapping stars with unbelievable precision, and then you have the LIGO, Virgo, and Kagra observatories. These are basically giant ears for the universe, listening for the faint vibrations from colliding black holes, actual ripples in the fabric of space-time.
And the progress here has just been, wow, unbelievable. When they first detected gravitational waves about a decade ago, it was historic, but the signal was faint. Now look at this chart. Compare that first signal to a recent one. We've gone from a signal-to-noise ratio of about 26 to 80. That's a massive leap. We've gone from hearing a whisper across the cosmos to hearing a clear, loud shout.
And that clarity, that gives us incredible power. With signals this clean, we can finally start testing some of the most fundamental laws of physics right at the edge of a black hole. We can check if Stephen Hawking's ideas about black hole information were right. We are literally probing the exact spots where our current theories are supposed to break down.
So where does that leave us? The hunt is on, for sure. We're dreaming up these incredible new ideas about reality and building these amazing machines to test them. But it all comes back to that final, huge question. If we actually do it, if we find a theory of everything, what is it going to tell us about who we are and what this reality is? Is space real? Is time fundamental? That right there is the ultimate prize in the greatest scientific adventure of all time.